Okay, so the next talk is about shortcutting for negative weight single cell shortest path by George Lee, Jason Lee, Satish Rao, and Jimkai Jan. And George will be the talk.
Thank you. And hello all, I'm George. I'm a second-year PhD student at CMU. I try to make graph algorithms run faster, and this is one of the few times I've succeeded for the negative weight shortest path problem. So for the people that have been in the room, this is the same problem that everyone has been talking about. I guess I should say it again, maybe. You're given a weighted directed graph and a source vertex S, and the goal is to compute the shortest path from the source vertex to every other vertex T in the graph. And in the most general case, the edge weights can be positive or negative. And yeah, that's the problem. And for the sake of this talk, we're going to assume that there are no negative cycles. So I guess with negative edge weights, it's possible that there are going to be negative cycles. Our algorithms can detect when this happens. So for the talk, there are no negative cycles. So as the previous talks have mentioned, the earliest work on this is the Bellman-Ford algorithm that runs in mn time. And in some recent breakthroughs, when all of the weights are assumed to be integers, this can be solved in essentially linear time now. And I guess now, essentially linear time and deterministically. So yeah, this is great. But in this talk, unlike in the previous two talks, we're going to be considering the real weight version. So we no longer assume that the weights are assumed to be integers. So to be more specific, this is called the add compare model or the real RAM model. So it's basically the same as the previous model, except you can't assume that the weights are integers. Yeah, so you can add and compare two numbers in constant time. Okay, so I see some people giving me weird looks, so maybe it's good to justify why this is interesting. So the main reason that this is interesting is because the previous two talks all described an approach based on graph decompositions that use what I'm going to call scaling tricks. You see, this is an approach that you basically half the negative edge weights at every iteration, and eventually all the negative weights are negative 1 over poly n. So then you can ignore these negative edge weights. In fact, Tashpan just made it even more explicit that without loss of generality, you can assume that all negative weights are negative 1 and all other things are integer. So with real edge weights, you cannot apply these tricks, which means that this requires development of new tools for the shortest path problem. And as a result, this will help us, hopefully, understand shortest paths better. Okay, I hope that's somewhat convincing to at least some people. So let me tell you about the prior work on this problem. So the Bellman-Ford algorithm still works in this setting. It still runs in mn time. And in a recent breakthrough result by Feynman, they showed that the Bellman-Ford algorithm is not optimal, and you can get a mn to the 8/9 time algorithm for this problem. And in a sequence of recent works, this has been improved to around mn to the 0.7. In fact, this final row is the next talk. So our result, the one that will be presented here today, is a completely new approach, to the negative weight SSSP problem. And we give an n to the 2.5 time algorithm, which is an improvement for dense graphs. Okay, so let me tell you about this new approach, which I'm going to argue is simpler. So the main idea behind this approach is this concept of shortcutting. So shortcutting a graph means that you're adding additional nodes and edges to the graph, where these added nodes and edges don't affect the distances that you're going to compute. But the guarantee is that the shortest paths use fewer edges. So this has been useful in parallel algorithms for problems like reachability and shortest paths, because for parallel algorithms, your like parallel runtime is essentially the depth of, or the diameter of the graph. So doing this pre-processing step using shortcutting helps for those algorithms. Okay, but that doesn't immediately suggest any way to apply it for the negative weight shortest path problem. So for this, I need to define this concept of h-hop shortest paths. So the h-hop shortest path is the shortest path between, let's say, S and T, using at most h negative edges. And it turns out that you can compute h-hop shortest paths in mh time. So if h is small, then this is a lot faster than Bellman-Ford. So given this definition, the natural definition of shortcutting, or a shortcutting approach to this problem, is you add nodes and edges to the graph such that distances are preserved again, but now shortest path use few negative edge weights. So for example, if you guarantee that after shortcutting, shortest paths only use h negative edge weights, you can just compute h hop shortest paths on the resulting graph. And this could be much faster than Bellman-Ford if h is small. So to be more explicit, what we're going to do is we're going to design a shortcutting algorithm that shortcuts any 3 hops subpath of some shortest path down to 2 hops. So now if you like consider an arbitrary, let's say, n hop shortest path, and then you just decompose it, or you just partition it into 3 hop subpaths, if you shortcut each of the 3 hop subpaths down to 2, you would have shortcut the entire graph, or the entire path by a constant factor. And now if you repeat this log n times, now you'll guarantee that all shortest paths have, let's say, 2 negative edge weights. Sorry, 2 negative edges. And then you compute 2 hop shortest paths on this resulting graph, and that runs much faster than Bellman-Ford. Okay, so that's the general approach. Now I'm going to tell you in a little bit more detail how we do this. So the idea is that for each negative edge, we're going to compute a forward and a backward search. So this will be denoted V out and V in. And what are the guarantees that we're going to have on the forward and backward search? What we're going to guarantee is that for every vertex U in the backward search and every vertex V in the forward search, the 1 hop shortest path from U to V through the negative edge, R prime, we're going to guarantee that that is negative. So there always exists a path from the backward search to the forward search going through R to R prime, 1 hop, negatively. And furthermore, if for a vertex U outside the backward search and a vertex V outside the forward search, and any path going from U that uses only 1 negative edge, R prime, and then goes to V, these are all guaranteed to be non-negative. Maybe let's say positive. So yeah, again, for U and V inside the searches, there's a negative path, 1 hop, 1 negative edge, negative path. For UV outside, this path is positive. That's the guarantee that we want on these searches. Okay, so with these searches in place, let me sketch how we can shortcut. So imagine that there's some arbitrary shortest path that goes on in the graph that goes through this R prime negative edge. And let's look at U is like the vertex that lies right outside the backward search. V is the vertex that lies right outside the forward search. So we're going to shortcut in a few cases. And the goal will be to decrease, like in this 3 hop subpath, we're going to try to decrease the number of negative edges needed. So in the first case, imagine that there's an edge, that this like final edge out of U is negative. In this case, what we can do is we can add an edge from U to R prime. So with suitable edge weight. So the path from U to R prime uses 2 negative edges. So if we add an edge from U to R prime that is also negative, that reduces the number of hops by 1. So if we stare at a 3 hop subpath, now it becomes a 2 hop subpath. Similarly, if the last edge, this edge going into V, is negative, we can do a similar trick. You add an edge from R to V. And again, the R to V path, subpath, has two negative edges. But like this one negative edge is, I guess, only one negative edge. Okay, and the final case is the last edge out of U is positive and the last edge out of V is positive. But recall the guarantee we have on the searches. The guarantee is that any path going through, like for any two vertices, U and V outside the search, this path is positive. So then what we can do is we can add an edge directly from U to V, which is going to be positive. So now this subpath with one negative edge is replaced with an edge of 0 negative edges, a path of 0 negative edges. So in these three cases, we are always able to shortcut down by a constant factor. If we do the shortcutting procedure on every negative edge, then we're able to guarantee that any path gets shortcut by a constant factor. So the total runtime of this shortcutting procedure, which I'm not going to prove to you, is n times the sum of the search sizes. And this is just because this U and V lie right outside the boundary, so you have to look at the neighbors of the searches. So you might be thinking, okay, if all of the search sizes are n, let's say, this runtime is still n cubed. So the final idea to make this all work better and faster than Bellman-4 time is a pre-processing step. We do some reweighting of the graph to guarantee that in the specific way we do the searches, that this total search size is actually n to the 1.5. Yeah. So with this pre-processing step, we can combine all these parts and get an n to the 2.5 algorithm, time algorithm. So to summarize, the first step is this pre-processing step I just told you about. It turns out to be a recursive pre-processing step, and it takes time, one recursive call to negative weight shortest paths. Then you can compute the forward and backward searches in n to the 2.5 time. This is just basically the volume of the searches. And we're assuming dense graphs, let's say, so the degrees are all upper bound by n. And then we construct the shortcut sets, as I described in the previous slides, also in n to the 2.5 time. And this guarantees that we can shortcut all paths by a constant factor. If we repeat this log n times again, then it's guaranteed that all shortest paths have 2 negative edges. And then we can compute 2 hop shortest paths on this shortcutted graph in just n squared time. And this gives a recursion that if you stare at it for long enough, it solves to n to the 2.5. Which is kind of true. I think it's actually not formally true. This is not the ideal recursion, okay? So, okay, I'm going to mention that in follow-up work by a subset of our group and also Sanjeev and Junkai, also in the audience, we can refine this approach to get an n squared algorithm for the negative weight shortest path problem. And this seems like pretty optimal for this approach, given that you kind of have to add n squared edges based on how we're doing things. So even if the original graph was sparse, then the final graph may be dense. Given that, there are a few open questions left. So first, can we improve this to n squared polylog? So this might seem not so interesting, but I have a reason for why it could be potentially interesting. The reason is, in this n to the 2.5 algorithm, our log factors are actually pretty decent. We have a log to the 2.5 factor. And so if we can improve the n squared algorithm also down to a polylog, there's a chance we could have an almost potentially, possibly practical algorithm for negative weight shortest paths, but maybe not so convincing. Another open question is whether or not there is a deterministic algorithm for betweenness reduction. So this is the pre-processing step in this algorithm, and it is the only thing that is common between our framework and Feynman's framework. And it is also the only part that is randomized in our entire algorithm. So yeah, if you can make that deterministic, you can probably get an n-squared algorithm that's deterministic. The final question is whether or not this preprocessing is useful for other problems. This is just, again, because it's the only step that's common to us and Feynman, so it seems moderately fundamental. So it deserves to be studied a bit more. Okay, thank you. So I guess you can, in theory, get to m. It's just n squared seems like the limit of this approach.
So let's then see it again.